Alright, so we ended on whatever problem that was, finding the area with, underneath the curve, with a infinite amount of rectangles and sigma notation using those rectangles. I think we were on number, I don't know which one we did, number 46 maybe. So the other ones, you know, that you do will have, it's just the same concept, except they will add on, you know, be like a cubic equation, like on 53, 51, a quadratic, but the same rules will apply. Now, once you get your formula set up and you plug in, you may have to use the rules of sigma notation to find, just like we were doing on the previous ones on like 37 we did, and 39 and 41, it'll give you that notation, and then you would use the rules to solve on that. So I'll give you all the rules for the test and with the mid-chapter assessment.
So like you would set it up just, or like you would put it into sigma notation and then use that to figure it out.
Yeah, so once it's in sigma notation, then you would use the rules like we did. I think we did that on 46, didn't we?
Yeah.
We used the rules like we've done before. And I won't give you like an extensive one with like lots of difficult rules. It'll
Like you would give us like 45.
Yeah, like a 45 would be like, okay, that's reasonable, easy enough to do, shows that you know how to use the rules, shows that you know how to set it up in sigma notation with the 3i over n or whatever we had, and then you factor out the 3 over n and blah, 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 and then you do the rule. So something that'll be reasonable. So it's not necessarily like complicated with the cubics, but the rules, you know, you have to pull out more rules and do more factoring and whatever. So, and you're also not gonna have like 10 of those on the test. It would be like, here's one, so you know how to do it. Then when we get up to the like 50, let's go to 56 on there. You guys had to do 56, and on 56, that is, well, I know you had to do 55.
Yeah.
Right, so 56, if we take a look at that one is g of y equals 1/2 y, right? And then that's on the interval of 2y, like that. Okay, so that interval. So then with this, we would look at, so it's now g of y equals 1/2 y, which looks a little confusing because typically we have g of x, right? And so in this case, in order to graph this, so if we go to graph it to get a look at it, we know we have 1/2 y. Essentially, you are stating, I mean, you can do an XY T-chart with this and say, okay, if I plug in now, instead of plugging in for X, you're just gonna plug in for Y. So you'd be like, okay, I'm gonna plug in 0 for Y, I get out 0. You plug in 2 for Y, you get out 1 for X. So just going in reverse. So it's 0, 0, and then over 1 up 2, like that. And then you have this line going like this, right? The other thing you can do on these ones to figure out the graph is, instead of saying g of x is the same thing as y, now we're saying g of y is really the same thing as x, and then you can just solve for y and saying y is equal to 2x, and then graph it that way, and that's like, okay, y-intercept of 0, up to right 1, up to right 1, all right? And then what we're looking at here is from 2 up to 3 and 4, right? And so we're looking at this area.
But once we get to like harder ones where it's like 4y minus y squared, we can't do that, right?
No, you could. But if, 4y minus y squared,
Yeah, it'd be a lot, it'd be more fun than how.
that would be a little more difficult on that, but you could, like on number 58, 4y minus y squared, that one is just going to be a sideways parabola. You could you could do an XYT chart with it, understanding that you're just going to end up with some sort of sideways parabola. So, and then so in this case, they're looking for what is the area between here and here. It's the exact same thing, except it's just in terms of y. Again, we're not doing the area of a trapezoid. We're doing sigma notation for this. So with this being said, instead of saying delta x, right, now you're just saying delta y, and what would delta y be? Well, delta y is going to be
over
4 minus 2 over n, right? N being the number of,
infinity, but
yep, so then 2 over n, where n is the number of rectangles that you're going to use. And then for the sum, s of n is equal to, right, we do our sigma notation, I equals 1 up to n.
and then change, or 2 over n times.
Okay, so 2 over n times the f of 2 over n, right?
Yes. So it'd just be 1 over n. Oh wait, no. So it'd be I over two.
So this is where, like, since we're starting at 2, like
Yeah,
I think
plus
we talked about, it's like 2 plus,
Yeah.
and then something.
And then would it be I over 2n? Is that correct?
So you're saying I over 2n.
Yeah.
So then if we plug in, well, I guess we'd have to think through how many rectangles we're doing. But if you had, let's say, what would be an easy number of rectangles to choose? 2. So if you were doing kind of like, you have to kind of work backwards. If you're like, we're going to pick, let n equal 2. So we're doing 2 rectangles. So if we're doing 2 rectangles, then we know, delta y is equal to 2 over 2, so delta y is equal to 1. So in this case, we know if you're having 2 rectangles, it's going to be here is the first height, and then here is the second height.
Mm-hmm.
So the first height would occur at, in this case, 3, and the second height would occur at 4.
Mm-hmm.
Right, is what we'd want. And so if you were stating, then if that was the case, and we said let n equal 2, let's not erase this, but we'll go 2 over 2, right?
Mm-hmm.
And then you're saying 2 plus I over 2 times 2.
Mm-hmm.
All right, so then this would be 1. That's the delta y, so the width of the rectangle is 1 here and 1 here.
Yeah.
And then times the height, so you're saying 2 plus I over 4. So this one will always be a constant once we determine what n is. Then this one is going to change, so this would be, if you plug in 1, you would be stating 2 plus a fourth. So
it would be 2n over I then? Or just 2i over n? Yeah.
2i over n, yeah. So then you're stating then, because that would just be up to and then a quarter wouldn't work, but up to, and then in this case, right, if we change that to, oh, that didn't work, 2I over n, right?
Yeah.
And so then we said n is 2, and so then it's just I, so then you're plugging in 2 plus 1 there, 2 plus 2. Yep.
Perfect.
So then we say, okay, here we go. There's our sum. So on like the test, honestly, if you got to that, that's gonna yield, and maybe I say, hey, for one of them, figure out the sum all the way using your rules. And then the other ones just set up our sum notation, and that's the bigger one, is understanding the base times the height and everything. So this is probably the more important part for me, is figuring out that you're going to be what that equation would be. So maybe we do something like that where you're not grinding on so many formula problems, I should say. Okay. So then let's go to 4.3 now, and then Riemann sums and definite integrals. Riemann, George Friedrich Riemann, I think, is who that was named after, the Riemann sums. And what a Riemann sum is essentially just adding up the rectangles underneath a curve for a Riemann sum. And it's the area underneath the curve. So Riemann sums is, in the definition of area given in 4.2, the partitions have subintervals of equal width. This was done only for computational convenience. The next example shows that it is not necessary to have subintervals of regular width. So I'm just reading on page 266, 4.3 for the Riemann sums. So in that, like a Riemann sum, the idea is that you don't actually have to have the exact same subinterval, but essentially when we have our subintervals, meaning of the same width, you know, if you had the area underneath this curve, you could say, well, I want this rectangle to be this one to be this. I mean, you could do that, right? You could add up some amount of rectangles. But as your number of rectangles goes to infinity, your widths are all going to 0. Right? So this one's really big, this one's really small, but as we tack on more rectangles, they're all going to go to 0. So with that though, it states that you don't have to have the same width if you're trying to find area with unequal widths. In the book, they talk about, on page 267, they have the width of the largest subinterval in a partition, which they use as a triangle, is the norm of the partition and is denoted by that double line triangle, and then which is equal to triangle x, like delta, I guess, there. And then if every subinterval is of equal width, then the partition is regular and the norm is denoted by. So a little bit of confusing notation. Don't get too hung up on this, but I'm just going to write this up here. What they're stating is the largest subinterval of a partition, delta, is the norm of the partition and is denoted by this. So if you saw this, what that represents is that's the largest subinterval of a partition. And if it's regular, that's called the norm. If it's regular, then it's equal to delta x, which is what we've been doing, b minus a over n. So most of what we end up dealing with is the regular notation. So we're going to be dealing with what we've already been dealing with right there. And number of subinterval in a partition approaches infinity as the norm of the partition approaches 0. That is, okay, so if this, the norm of the partition, if that's going to 0, that implies then that n is going to infinity, which would make sense. And what that's stating is like if the width right here of the largest subinterval, so like here, let's say if we were just dealing with these two, if the width of the largest subinterval is going to 0, if the norm is going to 0, then what we know is that if this width, the largest one is going to 0, that one's also going to 0, which means the number of rectangles is going to infinity. So not extremely important, but sometimes you see some of this stuff and notationally we'll make a note of it. All right, so now go to page 268, the definition of definite integral. So in this, it says basically what we've just been looking at, except now they talk about the right here going to 0, the limit as the norm goes to 0, and then they have the same sigma notation that we've been dealing with, except now they tack in this f of c sub I delta x sub I, and really what that is it is the same thing as what we've been doing. Is this is just a height for any spot along there, and then this is the change in x. And what this is stating is as the norm goes to 0, that's what we're talking about, meaning the largest subinterval, because you don't have to have all equal widths, but the largest subinterval is going, this is going towards 0. It looks really big here, but as that goes to 0, what it is implying is the number of rectangles is going to infinity. And so essentially you're just adding up all the sums of infinite amount of rectangles. So it's really the exact same thing. It's just explaining that they don't have to be equal width. Now, the whole c sub I and which is basically on the previous page, but you can think of c sub I is just referring to, again, some value, on a curve here, and this is c sub I, the height of the rectangle, f of c sub I. And then, you have some rectangle here like this, and then this is, this distance is delta x from here to here. So, okay, but really just look at it as basically the exact same thing as what we were doing. Don't let the whole minutia of it become complicated. One of the keys is that this notation stuff right here is going to equal, if you look in the book there, they have the integrable is the definite integral is also written now as this, and this is essentially now like what we're going to talk about, our cheater method. Okay, so f of x dx. So this up top here is essentially what we were just doing. As this goes to 0, what it means is all the rectangles' widths are going to 0, which means n is going to infinity. Okay, this is the height, and this is the width of all those rectangles. That notation can just be written like this with the Roman S, which stands for sum, and then A to B is simply telling you the interval that you're on. If this is A and then this is B, that's what it means from A to B. So it just means along the x-axis, you're going from A to B of our height times our width.
So it could be A, or it could be like B to A, like that doesn't matter.
Yeah, it could be B to A, it could be flipped, or it could be, we're going to do numerical values where it's like 5 to 7.
So it wouldn't matter like it was 7 to 5 on the notation.
The way the notation is, this has to be the lower limit, this is the upper limit.
It'll always do that.
Yeah, lower limit up to the upper limit, okay? So then, that...
Will always x values? Oh, will they always be x values, or will they...
No, they could flip it, just like we did that problem over here. You could be going from here to here,
Okay.
depending on what you're looking for.
But it would be like an f of y equation.
It would be an f of y equation. But most of the stuff we deal with are f of x equations. And when you're finding the area, it is finding, like, you know, if it's from A to B, it's just finding the area between the curve or the line and the x-axis. It's not infinitely going down there. Now, we do have some where it's like over here, and so you're finding the area. This would be like a negative area, this would be a positive area. So you can have, if you will, a negative area because it's negative areas of rectangles, which represents different things for problems we solve, okay? So when we look at this, then going down to theorem 4.4, this one gets used. Continuity implies integrability. So meaning if it's continuous, if a function is continuous, then it's integrable on that function. Meaning anytime you have a continuous function, right, that's continuous, right? As long as it's continuous, that means anywhere along here from A, if this is where our graph stopped, anywhere along here you can do the integration of it, meaning you can find the area underneath the curve anywhere along there. If it's not continuous for whatever reason, right, let's say it has then it's not integrable from A to B because there's this blank spot that you don't have an area. Now you could partition it and find the area from here and then, you know, all this area and then all this area, but that would be from A to B continuous and then from C to D continuous. You're finding two separate things. So all it just means is if it's continuous, you can find the integration of it, you can find the area of the rectangles. Okay, so then they talk about what happens where you have okay, the definite integral as the area of a region then is if f is continuous. So this is on page 269, theorem 4.5. This is an important theorem. It says if f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis and the vertical lines x equals a and x equals b, is this. So what we define now as the area underneath the curve is this. If f is non-negative, meaning your graph stays above like this, then the area underneath the curve from A to B is the integration, just like we've written, f of x dx. So this represents the area underneath the curve, defined by between the vertical line here and the x-axis and then everything underneath the curve. What this is back to, again, all that summation notation we were talking about. That is what's going to be happening here. But you're not going to end up having to do all the formulas. It's going to have this, like, if you will, the cheater methods for you. Okay. So then, two special integrals. Okay. So Nick, you were talking about A to B versus B to A, and you made an mention of that. There's two special integrals that they talk about on page 271. And the two special integrals are this. If you have the integration from A to A of f of x dx, that's just equal to 0, which would make sense is that there's no area.
There's no area.
You know, because you're only going from A to A. So you're not moving. It's just what's the area underneath the curve at this spot. There is no area. But then they have what is the integration from B to A, meaning if you're going from A to B. Now, this is important because of the way the
Comes negative.
yeah, the way the notation works, or the way the, if you will, the cheater methods, or I call them the cheater methods. Then if you're going backwards in the area, the way the integration formulas work is that, because you would say, hey, from A to B, this is a positive area, right? But when you do the formula, if you go from B to A, what you're actually gonna end up is with a negative
So
area.
you
The way
just
the
put the
formula is
negative
written.
out in front so that it gives you a positive.
Yeah, so then it's a negative,
But in reverse.
yeah, putting reverse A to B. F of x dx. So. Okay, so then those are two special ones, and then the additive f of, okay, another one is that this is if you have a function here like this, whatever, and you have, you know, from A to B, and then you tack on, what if there's a C in there? The integration of A to B of f of x dx can be split up into from A to C. So it'd be A to C f of x dx plus C to B f of x dx. So you can take a function, and sometimes it's helpful, depending on what you're looking at, to split it at a specified interval at C. And so you do the integration here to here, and then from here to here can be beneficial, depending on the problem you are looking at. Okay. Constant, we already know this, a constant can be brought out. Summation, like if you're doing adding two functions together, you can split those. So those two things are the same. So let's go ahead and go to page 273.
Alright.
And that is we'll do some problems. I'll give you your homework problems here in a minute. But these are problems that you.
Do we get the cheater method for this one or no?
We're not going to need the cheater method. I'll show you why at this point. What we're doing with this is just to understand the area of the underneath the curve. So with just this notational thing. So if we look at we're going to skip 1 and 2. Let's jump up to, let's take a look at number 4. Okay. So if we jump up to number 4. Now, number 4 says evaluate the definite integral by the limit definition. So on number 4, we have -2 to 3. Okay, -2 to 3, and then it is of the function x dx, right? Okay, so what they actually want you to do is to go backwards, if you will, and think about this, meaning what this is represented with our sigma notation. So if we go backwards in this, what we're actually going to be given is this right here is actually y equals x, right? And on the interval of -2 to 3. So when we go to do this, we would say, back to the sigma, notation, we're going to say, okay, what is delta x equal to? So if you think, okay, this is what I'm given, what's the sigma stuff going on here? And we would say, okay, what is delta x then? Delta x is going to be 3 minus the -2 all over n, right? And then we would state that this is 5 over n. Okay, so then we know, all right, this I is equal to 1 up to n, and then we know that we would have the delta x is 5 over n, right?
Yep.
And then usually that's written, you can put it in the front, usually it's written on the back end, is fine.
It would be -2.
So -2 plus, that's because we're starting, right? We have to go over 2 and then start our rectangles going up. just 5I over n, right?
Yeah. Man, how'd you get that so easy?
Well, because we know that it's 5 over n,
Yeah.
and so 5 over n times I.
Is that usually what it
Since,
is?
well, just since it's only going into x. We can do another one where it's not just x, and then, but yeah, it'll be that. So, and then you would plug in, you know, then you can go from there. And you could do the formulas out from there and solve. Now, they do have you do the formulas doing, hey, what's the sum of this using our formulas? And then you end up, I have the answer here, which we won't do the formulas, but they come up with the answer is 5 halves. Like, the answer of this is 5 over 2 plus 25 over 2n, and then you do the limit, right, as n approaches infinity, and so then you just end up with 5 halves. So there's the work to get there, but this is like the key. So what they're trying to get you to do is to say, hey, this is the same thing as that. But we're going to have a cheater method that helps us go from here to here.
Gotcha.
We're going to get there. Okay, so with that, let's take a look at number. You want to do a little harder one,
Yeah.
like number 8?
Yeah.
Let's look at number 8. Number 8 is -2 to 1, and then this is 2x squared plus 3 dx. So again, what they're stating here is, hey, you're given the equation 2x squared or cubed? What did I say?
Squared.
It's squared. I wrote cubed, but it's 2x squared. You're given 2x squared plus 3, and it's on the interval of -2 to 1. Go ahead, let's write some sigma notation from that. So go ahead, do the sigma notation from that.
Or wait, the rate of change is 3 over n? Yeah, 3n.
Okay, so we can at least hopefully we have delta x, right? What's delta x?
3 over n.
Yeah, 3 over
So delta x is equal to 1 minus -2 over n, so 3 over n. So then we know that, all right,
n.
sigma notation,
I equals 1.
I equals 1 going up to n.
3 over n times.
So 3 over n, and then No. I didn't write this over there, and that was lazy. It's really f of whatever you have in here, right?
Wait, what do we pick for? What was that f of what?
Right. Well, you're dealing with the original function. Now over here, since the original function was just x, this just went in for x and nothing changed. So here though, we need to figure out what are we plugging in each time.
I mean, don't we either pick -2 or 1 to substitute for x? No, it'd be I for x, right?
So we know
-2.
-2 plus, and then it's just, okay, 3i over n.
Does the 3 come from the rate of change?
Yeah.
Okay. And -2, that's just the beginning of the first.
And the reason why it's always, yeah, because that's the where we start, you have to go over
Right.
-2. The reason why it's always 3i over n
Yeah.
is because whatever n is, right, then you just plug in, you know, like I tells you you're gonna move it over, you know, the
Oh,
one.
but then that's not gonna give us the final equation.
No, but that's just, it'll always be like 3i over
Yeah,
n.
that's, but then we have to plug that into
Right.
that.
So
So
then
it's
you-
just gonna be 2 times
2
that
times -2 plus 3i over n
squared plus
squared.
3,
plus the 3,
all of that times.
all of that times 3 over n, yeah. So,
Oh, that makes way more sense now.
yeah, so again, on the test, now what they have you do in your homework is, and maybe I'll adjust a little bit of this, is maybe I'll say, hey, just get to here, and then, I mean, remember what we did last time, this is a constant, right? And we would bring the 3n out front, and then you could do the 3 over n would come out front, and then we worked with the integration of like this, and then, or not the summation of this, the summation of this. Then the 2 was a constant, so that came out, you know, we've done ones
But
like this
why'd you
before.
pick 2 as a constant?
Well, the 2 is a constant because it's right here.
That, okay.
So my concern isn't that we do a ton more of this work from here. I think if we're getting to here, that's good. So like on the homework problems for 3, 5, and 7, why don't we just, since in 4.2 you're working with simplifying this farther, right?
Yeah.
I think for 4.2 or 4.3, let's just say, can we get to here just with practice, understanding this is what's really going on, but we don't need to find the sum.
I feel like in 4.2, like none are gonna be, or none are as complicated as.
You have like a squared and a cubic one that you can grind
Yeah.
out. You don't have
But
to
they
do
don't
it.
get like, this one seems a little more
Yeah.
in depth.
Yeah, so let's stay on 3, 5, and 7 so far because you're going to do some of the odds. You don't have to work out what the sum is, okay? So then let's go to exercises 9 through 12, and it says write the limit as a definite integral on the interval a to b where c sub I is any point in the ith sum interval on that. And so if you look at number 10, this just is nice because they're actually not having you do the definition.
You say 10 or 12?
10. So they have where the norm goes to 0, which we discussed what the norm is. What the norm represents is I equals 1, 6. Just stick around just for a second. C sub I. Is that C sub I? Yeah. 4 minus C sub I. Quantity squared. And delta x. Aha! Okay. Journey. What this represents is as the norm goes to 0, your rectangles are going to 0. This is the same thing as writing the integration
That going to infinity?
like this. We don't have to write the anything going to infinity. They're just going to equal each other, the notation.
Gotcha. Oh,
So
so we're
the-
trying to transport it.
We're going to transfer it. Now the integration is going to be a little tricky. Let's just cover this when we come back. However, let's do 1 through 4, 3. Are you even on 4, 3?
Yeah.
Maybe. 1 through 47, Bob. And then, tack down there for some reason. Oh yeah, then, number 69. That one out there too. Okay?
Alright.
Then eventually, in 4.4, we start how this integration, we can do a cheater method, and then we don't have all this summation stuff. But good work. So we will we'll start there tomorrow, number 10.
Alright, thank you.